afternoon. Before we begin that, I just wanted to say a little bit about our plans for a discussion period today. Since it's such a lovely afternoon, the organizers are proposing that we all go over to the Free House, which is sort of just a couple blocks over that way. They have a nice courtyard in the back, which is open air. We can get, beer or soft drink, whatever you like, and I hope everybody can come. We'll have a nice discussion, relax there. If we get there around 4:30ish or so, it shouldn't be so crowded. I think we can get a bunch of big tables together. So that's the plan for discussion this afternoon. And our speaker now is Sida Wang, who's at Stanford, and he's going to talk to us a little bit about interactive language learning. So take it away.
Right. Okay, thank you for having me. I'm Sida, and my talk will be interactive language learning from the extremes. This is joint work with my advisors, Percy and Chris, as well as two undergrad who worked with me over the summer. So the goal of this research is to address natural language interfaces, and in particular the language understanding part. Currently, as speech recognition is working better, the understanding part is becoming the limiting factor and is often made fun of. So in Colbert's show, after a few rounds, Colbert said, "For the love of God, the cameras are on, give me something." And Siri replied, "What kind of place are you looking for, camera stores or churches?" So while it's forgivable that through the process of learning language that mistakes are made, currently when these mistakes are made, there is no way to correct them and learn from the mistakes so that they are not made for the next user. And this is our approach, which is to have systems that receive feedback continuously from users and improve through use. So there are a few reasons why this is necessary. Often you need to adapt to users. My regular weekday alarm is different from yours. And maybe people want a language interface for special domains where the language use deviates significantly. And also, we want to perform really complex actions, such as call Bob every hour until he picks up, stop after 8 tries, which is beyond the capability of current natural language interfaces. So we pose two questions. One is how can we learn from scratch really quickly? And the other is how can we learn and build up to complex and custom actions? And the first part deals with learning from scratch. One inspiration for this is the concept of a language game from Wittgenstein, who famously said that a language derives its meaning from use. And we instantiate a form of the language game. It's a goal-oriented activity where a language is a consequence of the parties trying to reach the goal. So in particular, it's a cooperative game between a human and a computer player. So the human player has a goal in mind, but cannot perform any actions directly, and must use language to communicate with the computer player. The computer player, on the other hand, does not know the goal, but can perform the actions, some particular set of actions. And furthermore, the computer does not understand any language in the beginning. So to succeed in this game, the human player must teach the computer player a suitable language and adapt to the capability of the computer. And the computer does the best it can to learn the language quickly through this interactive process.
Yeah. So does the human know what the actions are that the computer is capable of doing?
So no, the human also does not know what actions the computer can perform. But roughly there's a domain, so maybe the human can guess what kind of actions are wanted. Okay. So in particular, we do this in a blocks world.
So is this going to be one shot, or is this a sequence of many different related tasks that the
Yeah, so it's a sequence of related. So yeah, it's an iterated process. Yeah. Okay. So our particular setting is in a blocks world, where you have a starting set of blocks and a goal set of blocks that the human is trying to reach. So in order to do that, the human would produce an utterance, such as remove red. And the computer performs in the beginning just some random actions, but it returns possible actions in a list. So I wrote down some of the possible actions, but the human never sees these actions. It just sees the resulting set of blocks. Right, and from this list, the human selects the one he wants, and the computer learns from that selection.
Just a quick question. So does the human see the action being performed, or just the end result?
Just so the human sees the end result of the action, but not the actual program. Yeah.
Of each of the 4 candidate actions?
Yeah.
Okay.
Yeah. Right. I'll show you something more concrete. Yeah. So in this case, the human can just say whatever they want, and the system would do its best to figure out what's happening. So it could be Chinese or Pig Latin. Okay, so I'll show you how this works. Yeah, so in the beginning, we just need to perform some pretty simple actions, such as remove bra. And then, yeah, from the list, you pick, and that's remove bra. And now your computer should know what remove bra is, but that's not what we want. We want remove orange. Yeah, so you pick from the list. I was just scrolling down the list until you find the goal state, accept it. And right, so this starts with really simple actions like just removing a color, and it proceeds to maybe talking about the leftmost, rightmost of a set, add colors to another color. Well, I guess we taught it remove orange, so add orange is pretty natural. But otherwise, yeah, it should perform some basic generalization, right? So once it learns the color, then actions that takes colors as arguments can be learned more easily. And this proceeds in kind of increasing difficulty, and concretely, that's just based on the length of the logical form required until the human and the computer can together perform more fairly complicated sequence of actions.
Can you just say, like in the very first step, there is no connection between what's typed in and the candidates that the robot offers?
Yeah, in the very first step, it's just a random list.
Just random.
Yeah.
So then, maybe you'll get to this, but it seems surprising that the robot would generate in the first 1,000 things the thing that the human has in mind.
Right.
So.
Yeah. We'll get a little bit into that. Yeah, but I agree. Okay, so that's the game. And we'll talk a little bit about how the computer works. And the formulation is semantic parsing, which is converting language into logical forms, or in our case, really into programs. So in our logical forms has a few predicates like add, color, rightmost, leftmost, remove, some set operations. So notice that multiple actions can correspond to the same block configuration for any given for any given starting state. And we use parsing fairly loosely, where we basically generate logical forms from the smallest size to the largest to larger size, score all these candidates with a model, and use beam search to prune the set of logical forms that we are considering. And in order to score these logical forms, we use a log linear model with features defined over the utterance and the logical form. So, right. We really features are arbitrary strings in our case. Right. So for any given input x and z, you can define a function that maps them to any string, and the learning process just assigns a weight to the presence of that string. Except we don't really have access to the formula z, and instead we learn from the denotation, what we call the denotation, which is the result of executing z on the starting state, y. And to do that, we maximize the probability of all formulas that's consistent with the observed denotation. So we just update this loss function with eta grad. That's how learning works.
So the only parameters that are being learned here are the thetas, right?
Yeah.
And the features are the sort of individual features in phi are set beforehand.
Right. So the choice of features determines how well you can generalize, right? So for example, I give here you can just memorize x and z, right? That's the second example feature, which won't generalize very well at all. Right. But if you break down the features compositionally, then you can expect better generalization. Yeah.
So what's that sizes 10.5? That's English text.
Yeah, so you could say one feature, right, I'm just really driving the point that just by using this formulation doesn't mean all that much unless you specify which features you're using. So this particular case, we could have a feature that's just the size of the utterance versus the size of the logical form, and maybe you can capture things like if their sizes are too different, then perhaps it's not quite a good mapping. And that would be reflected in a negative weight. Okay, right. But the particular features we use, we wanted to generalize a lot better, so we break down both the utterance and the logical form into parts. So on the utterance side, we have unigrams, bigrams, and skipgrams of the utterance. And on the logical form side, really it's similar, except sorry.
So what would be an example of the logical form? Like, is it a tree or?
Right. So yeah, so the logical form, an example is just that formula is an example. Yeah. So and it has a tree structure. Yeah, so it's really very similar on the logical form side, but because we have a tree structure, we can do a little bit more than bigrams, where we can capture the local structure at each node of the tree. And the real features are just cross products between the two, right? So through learning, maybe you'll learn like whenever the token put appears, you should add something. Right, and put orange, perhaps add orange to something.
So what is this list of possible features?
So
add star star, how do you know that was a reasonable?
What is this list of features?
Yeah, so when you actually code it out.
Yeah, right. So based on the logical form present, you will generate add star star because add is just the entire logic, this logical form made use of the predicate add.
Okay.
Yeah. Yes.
And the predicates are known beforehand.
Yeah, the predicates are known to me and to the system, but it's not known to the human player. Yeah. Right, and through learning, you want to upweight features like put corresponds to add, and perhaps downweight features like put corresponding to orange.
So do you sort of greedily add more features as more examples are seen? Or
So really a feature is just a string, right? It's, in this case, that string.
Right.
And yeah, and if you see more utterances that contains unknown new words, and then you will have more features and more parameters in your model. Yeah.
Okay.
Yeah, and learning is just assigning weights to these features that are very free. And that's our computer model. And we actually tried to get a bunch of people to play this game. We got 100 Turkers to play this, and they produced just over 10,000 utterances. They were given fairly minimal instruction, and in particular, no examples to avoid biasing their language use. Really, all the instruction that they were given is the paragraph here. Yeah, and some player actually enjoyed the game. We'll measure performance based on how much scrolling they had to do, right? So if they were very successful at teaching the computer, then maybe most of the sentences generalize correctly, and they don't need to do very much scrolling. If nothing generalizes or things contradict with each other, then they have to scroll a lot to get to the choice they want. Yes.
So a way this could go kind of poorly is if the teacher kind of keeps on giving extremely simple tasks to the computer, right? Then obviously the computer will learn to do very well with minimal amount of scrolling on the part of the teacher, but at the end you haven't really learned anything particularly interesting. So how do you make sure that there are enough non-trivial tasks?
Yeah, so in some sense, there's a step limit, right? So you're given this many steps, and you have to, your complexity has to, yeah, you have to be able to accomplish it within that. Yeah.
Did you select how complex each task was, or?
Yeah, so that part isn't like very scientific. It's just a, yeah, kind of a level process. Yeah. And it's roughly based on the length of the logical form required. Yeah, but so essentially, in the beginning, you kind of teach it colors, and then teach it like things that require a few colors, and then require set complements, and until you can do everything. Yeah. Right. So in the bracket is the amount of scrolling that players had to do. And we are currently looking at the most successful players who didn't need to scroll very much. So they tend to be very precise and consistent, using the same term for the same action. But you can use English, or you can use some short form, which by using the short form, it's perhaps easier to be consistent. Then going down the performance metric, average players tend to be slightly inconsistent, using, say, reinsert, put, add for the same term, or in some case, because they don't know anything about the computer action space, just mismatch the action space. Right. So I guess I didn't really precisely define the action space, but basically it's represented using left, right, and set operations on them. So we don't really represent numbers. Or you could maybe represent numbers with like church encoding, but that's very long, and really in practice we don't represent numbers. So if you use numbers, we can't really do exactly what you want. but the system could still learn things like, say, number 1 corresponds to left, and the high number corresponds to right, and that kind of things. But that harms your performance. Then there are, the worst performing players tend to be a bit spammy, vague, or in some case just didn't bother to tokenize for the system. I thought I made minimal assumptions about language, which is just we have units that are tokenized, but sometimes they just give me a whole unit, and in that case the system doesn't really generalize. And that kind of gives you a baseline on how much learning is doing for you. So besides the English players, we had one player who used Polish and another player who used Polish notation. We observe players adapt to the task by becoming more consistent and more precise. So looking quantitatively at how well learning works, our full model basically gets, this is accuracy, so the percentage of times where the first candidate's return is correct throughout the game. So the best model that we use gets 33% accuracy overall, which is much higher for the top 10 players. And because you do, right, once you taught like remove red, you can use remove red, and memorize does around 17%. Okay, I think I'll actually skip pragmatics, which is just a way to make learning a little bit quicker. Yeah, so we can maybe talk about something newer and more exciting. Right. So since we took this game, the game was just online, and there were more people playing it, which gives us more data. And this is like very, very diverse data, right? Using all kinds of languages, English, various foreign languages, and computer-like languages. But you can note that they have similar problems, like occasional mismatch with the action space, and perhaps some tokenization issues. All right, so at least for this setting, we were able to learn from scratch fairly quickly, and we observed that people adapt to the computer. But there are some fairly obvious drawbacks to the approach. One is selection can't possibly scale well to the number of logical forms that grows exponentially in its length. And for the particular setting we were considering, each user has a private language. So even if there are many, many users using the system, it wouldn't continue to improve. And finally, while it might be a feature, because
arguably, if you have, if the others can learn from the better users, the number of people will improve the system.
I see. So if the worse users can learn from the better users, then the number of people, yeah, I think that you can modify the setting a little bit to make it the case. But I'm just saying for this particular work, we wanted just a very clean setting where each person is by themselves.
Right. My point is that keeping them in isolation is a constraint that you don't need to keep forever.
Yeah, of course. So we're gonna relax that. Yeah. But these are the drawbacks, which is really the motivation for our follow-up work. Yeah.
So maybe just before your follow-up work, Have you considered letting the players actually design their own teaching tasks? Like
Let them design their own.
This is sort of, they could even just invent their own Go and then, I don't know,
Yeah.
you can tell the computer like,
Yeah.
number 2 and then.
Yeah, very, very interesting. So I think we also moved a little in that direction too. So maybe you can see if, yeah, but I agree with you. There shouldn't be like restricted to some task that I imagined. Okay, so that's the motivation for our follow-up work, which we'll call naturalizing a programming language. Which is in some sense the opposite of learning from scratch, where we all start with a programming language. Yeah, and the goal is we want to handle really complex actions, and I don't see how you can do that by search. And yeah, and we wanted to do it in a community setting where people share whatever they taught, and the system continue to improve. And lastly, because ultimately you're trying to get a computer to perform the task, perhaps it's good to accommodate a little bit to the action space. Okay, so the
line was very similar to what Tom had in his talk. Move this meeting.
I see. Right.
Same task.
Okay, so yeah, then this is our solution, naturalization. So we see the system with a core programming language, defines the action space, but perhaps tedious to use. And then user would teach the system by defining new things, like providing feedback like X means Y. And in the process, we want to evolve the language to be more natural. And that's basically learning a programming language from data. So, right, so to be a bit more concrete, the core language is unambiguous and composes tractably. And the definition is something like a 3 by 4 red square is 3 red columns of height 4. And if you have this kind of supervision, the user is telling the system exactly how to generalize, and you don't have to observe many examples and infer how to generalize. So in some sense, this is the Montague approach to the meaning of language, where if we take his famous quote, I think one implication you can draw is he would say language derives its meaning from definition. Yeah, and we want to do this in a community setting. And the particular world we are doing this in is a voxel world, where each voxel just has attributes, coordinates, color. And we think of the world as a database with the relations and just a few domain-specific relations, like the directions, essentially. And we use 2 domain-specific actions, add and move. And the core language is basically designed to be more designed to interpolate well with natural language, but it has your usual programming language features like control flows. We really want to avoid explicit variables, so we use this formalism called lambda DCS, which basically makes tree structure join very convenient and variable free. So you can say has color yellow means everything that has color yellow, and you can do set operations. You can do has color of has row 1, so that means color of the things in row 1. And to further avoid having explicit variables, we have an implicit selection for the users to refer to. This is like the turtle in logo. to help people build up hierarchically, we have a few scoping primitives. All right, so that's the language. Most of it is just very generic and fits into the database viewpoint of the world, except for a few domain-specific actions and relations.
Can you say what this means?
It's just the current thing selected. Okay, well, yeah. So I'm supposed to show you now how definition works, how the learning process works here. Okay, so that's the interface, and I think it's fresh. So I want to do add palm tree, and this is just from the very beginning, right? It doesn't know anything about language. It only knows the core language. Sorry. Yes. So I might say add trunk 3, and still it doesn't understand. So this would be okay. And I can define add trunk. So perhaps then after I did the trunk, I go to the very top. I select some spaces besides the top, and add a leaf, right? So perhaps I think that's a reason. Maybe that's a reasonable palm tree. Okay, so we should have add palm tree now. Yeah, and so we use the probabilistic model to handle scoping choices. And once you have add palm tree, you can use add palm tree in further definitions. So perhaps I want like a row of palm trees. And I can do anyways, so a little bit tedious. So this is a row of palm tree 5 spaces apart, perhaps. Okay. Yeah, and then you can do this kind of things repeatedly. So it's, yeah, as you can see, right? Initially it's fairly tedious. I have to do the bracketing and basically writing a programming language. But so quickly it's getting powerful, right? I can use this pretty simple command to make this relatively complex action. Yeah, so basically you can define anything in terms of things that are already defined, tracking all the way back to the core language. And the model is similar to before, except now it's over derivations instead of just logical forms. And because of the change to learning from definitions, we can now handle much more complex denotations. But we still use learning from denotation, and now there isn't a big chance for random logical forms to collide in the denotation. So it's mostly to handle scoping choices, which is unintuitive to most people.
So after you typed in the previous thing, if you did something like add palm tree 10 spaces apart, would it?
That's okay. So let's see.
Or, you know,
Okay. So yeah, so it can generalize a little bit. Yeah. Right. So a derivation is just an object that describes the process going from going to the formula from the utterance, including information like which rules are used, where each component come from, categories, types, and the like. Yeah, so we still have various features, and now the most important one is probably just which rule you use, and that essentially turns your CFG to a PCFG. But in addition to that, we have, say, indicators whether the rule is induced or core. And because this is now a community setting, we want to capture a little bit about, say, which user likes things from which other user. So we have like friends features. And perhaps some users just generally do better things. So maybe just because the author is this user, the rule is better. So that's the author feature. And maybe people like rules that they author themselves a little bit better. So that's the self feature. Yeah, and the rest of it is pretty standard for semantic parsing. Just capture a little bit of context on top of the context-free grammar. Yeah. So the primary way of learning. Yeah.
Why is that a good heuristic? It's a heuristic that
Which
capture
is
a little context around the context-free.
Yeah. So some things are definitely not context-free, right? So add red left times 3, maybe that's your alternative loop syntax, right? Instead of repeat 3 and red left. But if the user has said like add red to row 5 times 3, then you can't just say like action times 3 is loop, right? It might be times might become a multiplication. So if you want to really model it, it's not completely context free. Yeah. Yeah. So learning is based through definitions, and I showed you what definitions look like. We want to induce a bunch of high precision rules from these definitions. And the way to do it is essentially a substitute matching part, right? I'll gloss over most of the details, but for grammar induction, right? So you have the input, the alternative loop syntax that you want, which is some action times 3. And you define it, say, in this case, directly in the core language, and you want to induce rules of the following form, right? So I just give you a few seconds to look at it. In this case, maybe both of them are fairly reasonable. The first one is higher precision, and the second one is more potentially generalizable, right? The second one the first one says it's this particular action, you can use this loop syntax. Whereas the second one says for any action, you can use this loop syntax. And you can't really, and the way you do it, right, find some corresponding parts in the derivation tree, substitute them with a variable, right, and build up the lambda formula. So there isn't like a generic way to be correct in all cases, because there is some context dependence, and so we use the same model that we use to score formulas to learn which rules to abstract. which is fairly similar to the Janlex approach from Zettelmeyer and Collins, except we are higher precision. Yeah, so basically, find the part that has the highest scoring and abstract that out. I'm glossing over a lot of details due to time because I want to show a little bit of results. So yeah, and the question is, we have this process, can people actually do it? So we got a lot of, again, a lot of Turkers to use the system and build structures for us. Yeah, and actually they built really impressive structures. Yeah, so the setup was we had a qualifier which asked people to build a fixed structure, and once they can build a fixed structure, there is a task where over 3 days they can build whatever they want. We encourage a little bit of conformity by running competitions, saying for each category, the best structure in that category gets a prize. But people don't have to build things in these categories. And to also encourage, because the point is really language learning, we want people to define things for us. So, and the rule, yeah, so it's very, yeah, so a rule gets a citation whenever it's used by another user. And we have a prize for people with the highest H index. H index, yeah. Okay, so it looks.
So the last bit depends on also how well your underlying algorithm is generalizing, right? Because if it takes an instruction and it can generalize very heavily on top of it, then it will use the.
Yeah, exactly. Yeah. Yeah, so we'll take a brief look at what these things look like. So, right, so the left-hand side are the structures that people built and the steps that they took to build it. You see it's pretty far away from the core language now. And yeah, and the right-hand side is a leaderboard of based on a citation. So score is the citation and impact is the H index. And it counts self citations. In this, I don't know if it's visible, barely. Yeah, so in this case, right, the rule was used 699 times, out of which 207 times were used by the user himself, and it defined go up 3 as go up 2 and then go up.
Question, so how do they evaluate other people's rules? Like it has some name, but it's not clear what it does.
So they don't really see the rules, right? So they type something in, and if they accept the result, then the rule gets a citation.
But so the system thinks user needs this rule, somehow guesses and proposes.
Yeah. So if someone else types like go up 3, then this rule might get used. Right. So.
I see.
Yeah.
The system guesses it may be the same thing.
System guesses. Oh, so right.
What is that?
So from each definition, one or more rules gets induced, and that rule has property author, the person who gave the definition. Yeah. Right. And now it's just a rule with some annotation. Yeah. And so if some other user types in another utterance, and to parse it, we need to use some custom rules. And so we parse it with a custom rule, which may or may not be correct. But if the current user likes it, the user accepts the action, and on accept, the rule gets a citation.
Yeah. So there's no visibility of rule action by new users. right? So they're just doing whatever they're doing.
Yeah. They just see, yeah.
Automatically creating that.
Yeah, they just see this interface when they do things. There's also no autocomplete on here, but they are free to look at the leaderboard and see like what they might be able to say.
Oh, but they can see the rules that other people have used.
They also have access to the leaderboard technically.
Oh,
But we don't show the rules, only the definition that derive the rule. Because rules has categories and so on, right? It's very abstract.
If they choose to use a named rule from somebody else, do they get the logic for free?
The citation for free, or the logic? Yeah, so if they use the rule from someone else, then that has whatever meaning that the other person, the definer, used. Right. So after I defined palm tree, then everyone else can use palm tree.
Okay.
Yeah.
So if you define tree and someone else like types in tree, but they don't like your tree, are they stuck with your tree?
So so yeah, you can maybe say, what's our thing, right? So I'll add palm tree, and you don't like my tree, and maybe you want like some yellow top, right? So maybe this is your like add yellow tree. Yeah, but then afterwards, if other people use add yellow tree, then I don't get any credit for defining a palm tree. It's only the final rule. It's all flat. Okay. Cool. Yeah, so that's roughly what it looks like. A lot of pretty good structures. Okay. Okay, so basic statistics for the experiment. There were 42 workers participated who built 230 structures. In the process, they produced around 64K utterances, and of which 36K were accepts. So note that each accept basically leads to a data point that's labeled by the derivation. And they gave just around 2.5K definitions, from which we induced 2.8K rules. And you can compare that with the less than 100 for the core language. Right. So is the process of naturalization happening in the process? Yes, I think the result is definitely yes. In the beginning,
what's naturalization?
It's whether the language has evolved from the core to what the user wants to use.
How are you measuring it?
So this is measured by the percentage of utterances that are still in core, or if it used induced rules. Okay, and then there's some amount that we can't parse at all. Right. So the amount that can parse at all drops slowly, but pretty quickly the amount of utterances that use induced rules overtakes the amount that use only core rules. Right. So in the end, on the right-hand side is accepted. The black line is for all users, and the colored lines are for some of the heaviest users. Right, but there's some difference in behavior, right? For example, the red users stick more with the core rules, whereas the purple user and the blue user very quickly went to their own space. Right, but in the end, for the last 10,000 accepted utterances, 77.9% used induced rules, and which means the utterance cannot be parsed in the core language. Okay. So I think that's pretty convincing in terms of whether the language use is evolving. And then we can look at as a rough metric of expressive power, we look at the string length of the program over the number of tokens in the utterance, which is around 10 for the core language. And where the black line is for the overall user community, we see this also grow very quickly as the experiment goes on. you also see a great variation between different users, right? So a very plausible reason for a jump is whenever they use like more primitive concepts to define higher level concepts, which leads to a big jump in the length of the program. But there's this one user who basically just used use core language or something. And the way this happens, right, it can be just short forms. It turns out people move a lot, and the core language for saying that is select left of this, which is fairly tedious. So people define things like left, L, move left, go left, even the less than sign as move left or select left. A bunch of other short forms for colors and what have you, right? So you can define things, you can define BRN as brown implicitly through an utterance like the following. More interestingly, they can pick a different syntax, right? So and is a set operation in the core language, and here the user wants to use it as the sequencing marker. A more succinct form for select a color, where color orange is really just a color value for the core language, and to get the set, you need to say it has color orange, and because it's fairly common, the user just define select orange. Yeah, different loop syntax. And almost a recursive definition, but one that we cannot generalize for GoUp 3. And more interestingly, there's some amount of higher level concepts. People define like a black block with blah, length blah, height blah. Flower petals in terms of flower petals. Things like a cube, get into position start, and so on, right? And you can see that used a lot in the leaderboard. Right. So if we look at citations, 1,000 of these induced rules got some citations, and here's a subset of the top 50 most cited rules. And the really highly cited are fairly simple things that everyone likes, like left 3 as a short form for like repeat 3, select left.
Question.
Yeah.
Is there, so do you see something like Zipf's law here as a function of frequency? I mean, you can see like loosely here. Obviously, it's not controlling for complexity. The frequency ends up putting pressure, evolutionary pressure on the length of the string.
Let's see. I think it's a bit different, right? So this is because either a new user just happens to think the same way as the definer, then they will use the rule, or they learned it from the leaderboard and liked it, and they'll just keep using it.
So for them to rename a rule.
Yeah, so if they want, they can redefine it to another syntax, but if they want to use exactly this one, then they'll give credit to the original definer. Yeah, but basically, I don't think of it as like pressure towards simpler things. It's just you need to do the simple options, simpler actions a lot more frequently to build stuff. And that's why, yeah, simple actions that everyone needs gets higher citation counts in this case.
Oh, question?
Yeah.
So, but maybe this suggests that if you augment the programming language with some simple primitives, these kinds of primitives,
yeah,
then there's nothing much more to do in terms of naturalization because everybody has.
Yeah, that's possible, right? But yeah, it's like what kind of diversity, right? Do you want to consider all the possible ways that people want to say it by yourself, or do you just want to, or can we just provide them one way to say it, and then they can figure out how they want to say it in a way that they like better? Right, and so yeah, but in addition to that, right, you also have these like fairly complex concepts in here, right? This one probably require either 2 loops or 1 sub-concept, right? Yeah, and we can't pause it. So this is like kind of maybe like a library for your language, and we don't want to build that by hand for sure. I think even anticipating all the syntax by hand is
that once you run this experiment, you learn the simple customizations,
right.
And beyond that, it may be very hard to.
Yeah, so that remains to be seen.
Right.
Yeah. Mm-hmm.
So in the end, is there only the global vocabulary and semantics, or can each user have their own version of, build a tree?
Yeah, so it's not, So it's not so good if people conflict with each other, and then their friends feature will get downweighted a lot, but it's still in theory possible. But the hope is, right, there might be many different versions of flowers, and we'll support all of them. And when people type in add flower, there will be a list of different flowers they can add.
So you could have flower defined with multiple.
Yeah. So the parser definitely supports ambiguity. Right. Okay. So the goal was really to bridge the power between current natural language interfaces with the power of a programming language in order to handle complex actions. We do it in a shared community setting. And hopefully this can lead to language interface that's good for beginners and experts alike. Yes?
Yes, this is really, really quite interesting about how jargon or like a kind of pidgin language develops.
Right.
I'm wondering if you're already seeing subdivisions between types of tasks and like if you're building a building, is the language of the jargon starting to emerge from your organic.
Yeah, I think it definitely varies a lot by users, right? So, so this user really likes the Go syntax, right? And other users barely use it. In terms of just the domain, we don't quite have, I don't think we observe big differences between the objects they are building. Perhaps the parts are not quite that generalizable yet. Yeah, but you definitely see big variation between user preferences. Okay, and so we cover 2 different extremes. So in the learning language game setting, we start from scratch, and anything goes. The system just tries its best to figure things out. In the naturalizing programming language approach, we start with a full programming language. One where we had a private language, and one where we had a community with some user modeling using selection as supervision versus the more powerful definition, but more powerful but also more cumbersome definition as supervision. But that allows us to build up to more complex actions and concepts. So in one case where we use learning from denotation to do most of the heavy lifting, and in doing so, we are fairly language agnostic. In another case, we use grammar induction to do the heavy lifting and parse in a very precise way. So unless there are precise rules applying, we don't parse. So we tried to apply the same approach to a calendar setting under the same language. There's a blog post I will point you to, but won't say much more. Yeah, so the goal of our research is really to enable a better language interface with the computers as speech is getting better. We explore two, I think in some sense, opposing settings. And one is perhaps the Wittgenstein view, where language derives its meaning from use, and the other is the Montague view. It's not a direct quote, but perhaps language derives its meaning from its definition. Yeah, and that's my talk. Thank you.
I was just curious a little bit in the different experiments. Do you have any idea about the backgrounds of your Turkers and how experienced they were as programmers themselves? And I'm just thinking like it'd be great to try this out with school kids of different ages and see how non-experts might.
Yeah. So I think by and large the Turkers are not experts. Before the qualifier, we did a survey where they were asked for their programming experience, and roughly, I think 2/3 said no, and roughly 1/3 said some experience. But I don't have the exact number with me right now. Yeah, I guess in some sense, the people who can program pretty well can find a better job nowadays than doing Turk all day. So you can be fairly confident. Yeah. Yeah.
So I'm wondering how important is the curriculum, the sequence of tasks, say in the first part, for example, where initially nobody has really any information, and so you have a monkey and typewriters kind of problem. You have people just having to type random things and hope that their intent is close enough in the list that they'll see it. And so you have a kind of constrained domain, then you have a sequence of those. So is that like a key design decision, or would it just work to make up any old combination of things?
I think for that part, it's an important decision. Just because partially it also communicates via the goal what kind of actions you can do.
And the name of the first task was, I forget what it was. Is that what you mean by goal?
Oh, like
basics.
Yeah. I mean the contrast between the start and the goal state, right? Partially communicates what actions are available. Yeah. Whereas, I don't think that the linguistics the names here matters at all. But yeah, so and so that this thing suggests that maybe like left is important. Yeah, so I think that makes it significantly easier. Whereas if you just start people in the wild, then they'll have a much harder time.
It's some kind of it's showing all the gradients, right? Each atomic action can perform this gradient, right?
Yeah, it's roughly through teaching, right? Some really short logical forms, and then some simple compositions, and slightly more complex compositions. So this is like all but cyan, right? Yeah.
How maybe of having in a domain such as this, having the algorithm or the computer generate the examples that it wants sort of the human translation of, and then sort of automatically getting learning that way rather than you having to hard code like this.
So you have two tasks where for the first one you get some human.
Or like have the computer generate all the examples. Or all the.
Or generate all the problems.
Yeah, we should try to get more coverage.
I see. So like all possible logical forms.
Or try to cover enough of them.
Okay. Yeah. You can definitely do it more systematically.
Did you try difference? You only did one experiment, so you didn't try difference starting configuration.
Yeah, but this is right. But the possible sequences is a big space to explore. We just picked one, and not yeah. I don't think we spent that much attention on that.
All right, well, let's say so.
Thank you.